narratability breaks down both with the wave function realism, the old ontology, and with the space-time state realism, the new ontology. But nevertheless, this failure of narratability has different status in the two theories. In wave function realism, it's strange, whereas in the space-time state realism, it's not strange at all. It's something more or less you would expect, because it's not worse than non-separability that you had anyway, that we were aware of right from the start. Because here the situation is just that information about what happens on these hypersurfaces does not give you all of the information of what happens on these hypersurfaces. But that's not different in any essential way from saying that, okay, let me compare these things. These are the horizontal hypersurfaces. Now compare with that. Oh no, I think I need to draw it in the same picture, otherwise I cannot make it understandable. Consider the following. Okay, I'll try to draw it in this way. Okay, consider this kind of hypersurface. We just take two pieces of hypersurface, and we know, of course, that the state here and the state here together do not tell us what the state on the union of these two pieces of hypersurface is. So that just suggests that when we look at the union of these two hypersurfaces, that we will get some new state on that, some new information about that. But actually here it didn't play any role whether we tilted that or not. So it's actually the same as looking at this hypersurface. So that's why in space-time state realism there is no big deal about this. Next point, appearances. So this is about deriving from space-time state realism how that theory would appear to its inhabitants. So to derive kind of the ordinary quantum predictions. The reasoning here is essentially the same as in any other version of Everettian quantum mechanics. Namely, I can write it like this. So decoherence plays a crucial role, and decoherence leads to the situation that the density matrix associated with the region A, where A is not too small and not too large. Let's say A is something like, if we think of something like Schrödinger's cat, it's something like the region where the cat is, or like where a measurement pointer is. Good. So that the state in that region will be a mixture, or in many relevant cases, it will just be a mixture of states that are quasi-classical. Like one state being a dead cat, another state being a live cat, or one state being pointing here, one state being pointing there. Quasi-classical state. Good. Now, from then on, we just obtain that for the observers in such a world, they of course they're part of these quasi-classical states. So to them, they have the appearance of a pointer pointing in that direction, or of a cat being alive. Good. End of David Wallace. Yeah, I feel a bit like an actor now. Okay, start my comments. Good. First, I'd like to make a remark on this issue about the particle position representation in quantum field theory. I think the problems are overstated. First of all, the configuration space here. Configuration space. So what Wallace said was that the configuration space is kind of strange, unnatural. Let's have a look at what it actually is. It's a union over n from 0 to infinity of R3n, some appropriate configuration space, or for when we talk about identical particles, then it's appropriate to mod out the permutations, to identify configurations that differ only by a permutation of the particles. So the space that we get in this way is just the space of all subsets of R3 with finitely many particles, finitely many points, I should say. So in mathematical notation, it would look like this. So now borrowing a word from Prior, I find this very beautiful. This is a beautiful space. It's very easy to define. It's the space that comes up naturally when you talk about configurations in three-dimensional space. This is just the space of all finite subsets of R3. I don't find it weird or strange at all to have a wave function defined on this space, or to have a theory that deals with this space, or to have configurations in this space. Next point. Are particles fundamental, or are fields fundamental? Well, first of all, that's not so clear. You see, on the one hand, people talk about field theory. On the other hand, people talk about particle physics. So it's even not so clear whether kind of the average physicist thinks of it as being essentially about fields or being essentially about particles. It seems that the ordinary physicist kind of uses both pictures, and after all, I mean, we are the people concerned about what should really be the fundamental thing. So it seems like the question is upon us what should be regarded as fundamental.
I think a thoughtful physicist would say that that's not a good question. It's
okay. I think that adds to undermining the argument that in quantum field theory you shouldn't be allowed to talk about particles. And we add kind of some more superficial, fuzzy arguments to that, like at accelerators at CERN, everybody talks about particle collisions. So it seems clear that at least for some situations, it's kind of more natural or more appropriate to think about what's going on in terms of particles rather than in terms of fields.
So that's not David's claim. David doesn't say you can't talk about particles. In fact, he's in print arguing that you can talk about particles in quantum field theory against people who say you can't. It's just he says they're not fundamental. He says they're emergent entities. So any considerations about how people think heuristically in terms of particles or talk about particles in particle physics can't tell against his claim, because the claim is about particles not being fundamental.
I think that
Sorry, maybe I shouldn't interrupt that. It just seemed very tendentious when you said,
I mean, can I ask a
there's an
related
explication
question?
of David that he says you can't talk about particles, and he definitely doesn't say that.
What if somebody says here's what they have in mind by seeing the fields as fundamental? I mean, you know, we've been talking about wave function ontologies here. Maybe none of these are fundamental, but the idea is something like fields play the role in the second quantized version of quantum mechanics that particles do in the first quantized version, that role being they're the enduring objects who, such that it's changes in their state, but not in their existence, that changes in the world are about.